That's always one of the most difficult things. Like, when people like ask you, are you good?
That's an easy answer for me.
Compared to this team, yes.
Yeah, people are like, you played in college, were you good? Well, how do I answer that question in a non-prideful way?
Yeah, I'll be like, yeah,
I
was
didn't
okay.
break my arm.
UConn 4 years, quarterback,
In college though.
Iowa coach.
That should define that.
Yeah.
A couple times.
I just put chemistry.
Alright, here we go. So we're going to continue on with the bonding. But before we can get any more deeper into the types of bonds, which is what we're going to do, okay, we do need to review some things. What's so funny? Chemity. Okay. So, if you guys recall, identifying the three types of bonds has a lot to do with where they're located on the periodic table. Why do I say that?
Oh, my brain thought I was writing my name.
Okay? So, please pay attention here. Let's focus. So, in reality, the best way to identify ionic, covalent, and metallic bonds is by their electronegativity values. That's the best way to do it. But we can actually clump it up into a much easier way of doing it, and that's based on whether they're metals, non-metals, or both. Okay? So we need to review where the metals are up here.
Where do metalloids bond?
We aren't going to talk too much about metalloid bonds. Okay? We're going to stick with the most common stuff. Okay? So, where are the metals located? Everyone should be yelling.
Left of the stairs.
Tanner, are you with me?
Yep.
Are you sure?
Yep, I'm with you.
Alright. Left of the stair step, there are a few exceptions.
The
Aluminum.
aluminum.
Okay, aluminum is on the stair step or adjacent, but it is definitely a metal. And then this little guy up here is a what? Non-metal. Okay, it's really important because we can make a quick distinction on whether it's ionic, covalent, or metallic based on their location or what they are, metals or non-metals. Okay? And then non-metals are where?
To the right.
To the right but not adjacent. So is that a non-metal? No, what is it? It's a metalloid. Okay? Come on, give me some more engaged stuff here. How about this guy? Metal?
No.
Metalloid?
Yes.
And these guys are your non-metals. Okay, very important. So here are your three types of bonds. You should remember this.
Oh!
What?
She can't figure out why I just didn't die.
I realized.
So here we go. Three types. Covalent. You should remember this, but I do need to review. Covalent bonds are ones where their electrons are being shared. We're going to talk today how they're not always going to be shared equally. Sometimes they're shared equally, sometimes they're not, and we have to give them a little different name, and they act a little bit differently. Ionic bonds, if you remember, are when an electron is given by one and taken by another, and what does that result in? How would they be held together then if one gives an electron and one takes it? We don't know? So sodium gives an electron and chlorine takes an electron. How are they held together?
Yeah. Well, they're opposite charges.
Okay, when you're giving electrons and you're losing electrons, or you're gaining electrons, I should say, you're going to have opposite charges. Those opposite charges do what to each other? They attract each other.
So they become stable, but they still have a charge.
The overall molecule, or in this case formula unit, would be stable, but the individual parts have charges, yes. This is why, guys, this is why ionic bonds are much stronger, is because you have a very strong charge holding them together. This is why they're much stronger than covalent, because covalent, they're either perfectly sharing them, and there's really no charge distribution, or they're one's taking a little bit more, but not enough to make it strong enough to take completely. Do you guys realize that ionic bond isn't really even a thing? Because it's really just a really, really strong covalent bond.
That's what I was thinking.
But we give it a different name because it acts quite differently.
Oh, yeah, I get it.
So what I'm saying, like, remember how I said that this guy, the electrons in this guy aren't right smack dab in the middle? Why was that?
Electron.
Yeah, because fluorine was more electronegative, so it pulled the electrons a little bit more in this direction. Well, what if, because the electronegativity of this is like 2.0, and this is like 4.0. But what if I had cesium with fluorine? This is 4.0, this is like 0.7. That is so strong that the electrons, we pretty much say, just sit over here with the fluorine instead of even with the cesium.
Are we gonna mark that with our little structures this time?
Okay, but what I'm saying is ionic bond is just like an extremely polar covalent bond. Is really what's happening, but there's a point where we say it's so strong that we give it a different name. Does that make sense? Okay? And then the metallic bond, so this should make sense. We're gonna summarize all this at the end, but this should make sense that the differences in electronegativity determine how strongly they're held together and what happens with their electrons. So everything can be explained from an electronegativity standpoint. Yes?
What if boron bonded with whatever Bi is?
Bi is bismuth?
Yeah.
Where is it?
It's 83. Wouldn't it be more? Bismuth is more electronegative than boron, right?
Yeah. As you go down, it gets less electronegative. Because they radius is big.
But it would.
I would say it's more down than this to the right. So I would say that boron's actually more electronegative. But I could be wrong. We could look.
Would it still be?
Let's find out.
Ionic though? They
Those guys probably will not bond. They're too similar in there. Where are they? I'm just curious now that you said that. Oh wow, yeah. Boron is 2.0, bismuth is 1.9.
That's crazy.
Do you see why I have you do both up and over trends like at the same time? It's too difficult to know for sure. Because the trend isn't perfect, guys. Right? The trend for electronegativity isn't all like every time you go to the right it's bigger. Or every time you go down it's smaller. It's not always the case. Right? For example, krypton having an electronegativity of 3.0. Okay? Alright, now the metallic bonds. This is typically between metals. So you should note that nonmetals have high electronegativities. And I'll just represent that with En. If you have two guys that have high desire for electrons, do you think one's going to give it away real nicely?
No.
No, so they're going to share. But if you've got an ionic bond, metals tend to have low electronegativity values. And nonmetals tend to have high electronegativity values based on where they're located on the periodic table. Do you see why metals tend to want to give electrons?
Yeah.
And nonmetals tend to want to take? Well, what happens when you have two things that have low electronegativity values? How is it in the world does that work? Nobody wants them. So what do you think happens? It's really interesting because this is why things that are bonded metallically are really good conductors of electricity.
Oh, I can remember.
Okay, so like imagine you guys are like the positive nucleuses of metal atoms. And I'm just one of the electrons that Trinity has, and Trinity's like, I don't want it, so I'm just like wandering about here. And I'm just, as I go by Brevin, there's probably another electron that's following behind me.
So
basically we're all like just standing together and just like shoving the electrons.
Yeah, pretty much.
Hot
Yeah,
potato.
it's like a hot potato.
Potatoes.
But you need the electrons there because if I wasn't here at some point in time, what would happen to these two positive
Positive
charges?
charge.
You
wanna
get two
push.
positive.
You guys would probably break apart, but since I'm moving around so fast and the electrons are rapidly going crazy, as soon as I leave, there's probably another one following behind me.
We always need a little bit too.
And so you can see why things that are metals tend to conduct electricity really well, because they already got electrons that are freely moving wherever they want.
I never thought about that.
But covalent things tend to not want to conduct electricity at all because they're both rigidly holding their electrons so tightly. I want these electrons, and so they're sharing them, but they're like, I'm not willing to give. You see what I'm saying? That's why nonmetals, when they bond, don't conduct electricity very well. The hot potato bond, that's fine. Okay?
Well, they call it the plum pudding model, we could call it hot potato.
Yeah, sure. Alright, we're going to focus on the covalent here. Okay, I think I alluded to this a little bit yesterday, this idea of polarity. Okay, so there's such a thing as nonpolar and polar. So first off, polarity just means opposite regions of opposite charge. So let's start with this guy that we've shown before. And we said this one has a high electronegativity.
So it would have a high polarity.
And this doesn't necessarily have a low, it's just medium. So since they have a difference in electronegativity, you see a non-equal sharing. But this isn't low enough that it's not going to be like, hey, you can just have it. Does that make sense? Okay, so what you have is these electrons do spend more time closer to that fluorine. So therefore, this side becomes partially negative. Do you see how it's not a full negative? Does that make sense why this is not as strong of a bond as like an ionic bond where it's completely negative? It's just a partial negative. And this is partial positive. Okay? The strength of this bond,
Partially.
yeah, this symbol just means partial. It's a Greek symbol. I don't remember what Greek symbol it is. But, okay? So the bigger the difference in electronegativity, the stronger the bond. Because the more charged it is. Okay? Now, if they were to be shared completely equally, so let's just say like hydrogen has your one valence electron, this hydrogen has one valence electron, and they're exactly identical, correct? So they would pull exactly the same amount. They both have the same electronegativity value. So when you form this bond, in theory, these electrons are going to be perfectly in the middle. Now, do you think it's actually going to be perfectly in the middle? No. Do you think electrons are just going to just sit there? No. And actually, you're right, they don't.
That's probably, you get into quarks and stuff, and protons, some protons have more quarks than others. Yeah. And so you got it.
Well, really what's happening here is, notice the guys that are diatomic, most of the diatomic guys, and a lot of these guys over here, are gases. So like as we get down, they don't become gases because of something we'll talk about in chapter like 11. Because what's happening here is there really isn't opposite regions of opposite charge. But what actually can happen is at any given time, these electrons could maybe shift one direction and create a small polarity. Well, then that creates small polarity in the next guy and the next guy. But since this is such a small force here, this is why hydrogen gas typically isn't in the liquid or gaseous form, because they don't have the polarity needed to hold them together. Which is interesting. But as we get to bigger molecules, these guys have so many more electrons that you start getting that charge distribution started going one way, you see this domino effect. And we'll actually talk about intermolecular forces in a different chapter, but it's really, really cool. Right? Now we'll talk about how you test for whether a molecule is polar or not. You can actually do it with a visually, but I'll tell you that when we get to Lewis structures.
I remember I didn't get this at all last year, now it makes sense.
Because last year, you know, as physical science students, it's my least favorite class to teach because it's all vocab. I have to just throw vocab at you because you need to know the words before I can go deeper into them. And it's really frustrating because sometimes I'm like, I can't explain the why. Like the other day, I was doing electron fill order. Do you guys remember like you fill with 8, then you go up an energy level, fill with 2, go back and fill with the rest of the way? That has everything to do with the SPDF and filling order that we went over in class. Do you think I have time to go over, hey, here's the F, B, D, and F sublevels? I don't have time to explain that in physical science. I just don't. So, it stinks. I really dislike teaching physical science for that reason.
I'll teach it.
You won't like it either.
Yeah.
Okay. So, we're going to end with this. Electronegativity values. I think you guys are starting to see that electronegativity values are really what tells us what type of bond is forming. Okay, so we're going to fill a little graph out here. So I think you should have some space there to fill out a little graph that kind of puts all this stuff together and how it relates to electronegativity. So first we'll have types of bonds. Okay, you guys should be able to identify the three types pretty quickly. What are they? Okay. Actually, let's make it 4. Let's go ionic. Let's go polar covalent. Non-polar covalent. I want to throw metallic in here. We'll do it. Okay, that's the first part of this little chart here. Okay. And we'll go how to identify. Right small, sorry. That's what I kind of like. Maybe we should have had you like right a little bit to the right of the next lesson's heading. So you have more space to go down. If you need to write it on a separate piece of paper or something, that's fine. And maybe I shouldn't have put metallic in there. Okay, how do I identify it's ionic? Just quickly. How would I be able to look at something like CaCl2 and tell me just by looking at that whether it is an ionically bonded, covalently bonded, or metallically bonded? How would I be able to just look at that guy and tell? Where they are on the periodic table. Calcium is where? What is that?
Metal.
Metal. And what do we got? Chlorine?
Non-metal.
So if you got a metal bonded with a non-metal, what is it?
Ionic.
That is the quick way of figuring it out, but remember, it really is determined by this, which we'll get to.
Wait, so we don't write it non-metal?
Yeah. Now, polar and non-polar covalent are both still going to be two what? Non-metals, but they're going to be a little bit different. And then lastly, metallic would be two metals. Now this is the quick way of determining this, but please, it's going to do you much better here to be able to know the why. Really, those are just identifications, quick identifications. It's like using your calculator versus knowing it in your head. Now I want you to be able to speed things up because we're going to get to hard, more difficult stuff later. But still, it's really important to know the why. Okay, now remember, where's my metet? Metet?
Doing the tat.
Metet?
I was looking at that too, I was like.
Remember, what does a metal typically have from an electronegativity standpoint?
Low.
Low. And non-metals tend to have
High.
high. This is why they typically give and take.
So high low.
I would say the difference between them would be high. The difference between a low electronegativity and a high electronegativity is going to be high. And an example of this would be like NaCl. I know we don't show NaCl bonded like that, but this has a low electronegativity. This has a high electronegativity. And this is why this guy gives and this one takes. One doesn't want it, one does. Now, is it in reality a complete giving and taking? No, it's really not a complete giving and taking. It's just so unequally shared that that's what we say. Does that make sense? Okay, polar. I would say this would be in the medium difference. Let's give you an example like HF. Hydrogen doesn't really have a low electronegativity value, so it still wants it.
So it's shared, but more so on the fast.
I know you guys probably don't have enough room. I apologize. I should give. Oh, good. Because this is pretty important, and because this guy doesn't have a very, very low electronegativity and still wants it a little bit, it still shares, but it just doesn't share how.
As much as a.
Yeah, it's not going to be equal share.
metal.
Not shared equally. Okay, well what if I got some non-polar guy? Let's say, let's just use the, why did I?
Low.
I'm not gonna say low, I'm gonna say same. You guys understand what I mean when I say the same electronegativity?
That's the same element.
Okay?
So it doesn't have to be the same element.
Wait.
Well, no element.
It doesn't have to be the same, but there's not many guys that have the exact same electronegativity.
They just have similar.
So you could have like 100% covalent bond.
Yes, you can in theory have 100% covalent bond, but there's no such thing as 100% ionic bond. Because nothing actually completely gives. Does that make sense? Everyone understand what I'm saying here? I can have 100% covalent because I can have, well, for the most part we say this is perfectly equally shared. We know that electrons do kind of still move around, right? But this isn't ever going to completely give and take. But we make a cutoff distinction that says once there's a big enough electronegativity difference, it's so unequally shared that we pretty much just say what? They give and take. In reality, that isn't exactly how it works, but we have a cutoff, and that cutoff is usually here. Anything lower electronegativity than hydrogen is actually considered a metal. And that's where we start getting our ionic compounds. Okay, last one here. So if I were to say, notice this trend here. I would say increasing ionic character. What do I mean? What do I mean by that?
You mean that the So like as you go up, it more
The difference.
takes
Yes.
an electron.
As my electronegativity differences increase, what you see is it increasingly becomes more polar. Hello? You were right. I forgot about that. No, they were here. So it was Steven and Brady. Yeah, Steven, Bruce, and Brady. No, they were here. Yep. Alright, last one. I'm going to say low here, but this is a little bit different because since you guys understand how this trend kind of is completely different than this, because what you have here is, let's just say we're I don't know, iron and let's just say an iron bond. They both have very low electronegativities. And I know they are the same, but they don't want. That's the difference. These are the same, but they still want. Does that make sense?
Yeah.
Since they don't want, what you get is a communal sharing, even though it's not by choice. It's the hot potato idea.
Figure that all out this way.
Did you guys know that the types of bonds really have more to do with electronegativity? But we just quickly identify it with this because it's easier?
Yeah.
Okay. You guys ready?
You get the
Yeah, I did that. Okay, great. I knew I was going to do that.
I was like, you know what, fun.
What?
I have legs!
Thank you. Woo, okay. Everyone gets grace on homecoming week.
You're a knucklehead. I don't give you grace.
Knucklehead.
Can you shut that off?
Just turn it off.
That button.
Red button?